clusters and determine their personality by looking at their scores and interviewing them, she devised an intervention strategy for one of the groups. One of the groups, their defining feature was they had a lot of students that worked very hard and were dedicated, but they were just really bad at exams. Like, I'm sure people who've taught before definitely encountered students like that. So for those students, she ran a test-taking seminar where they came in, like, I think about once a week, and they worked on their test-taking skills. And the students that did come to that did show improvements in their exams. And another application of her work is that by knowing how to classify students into one of these 5 groups, she determined whether it was more appropriate for them to enroll in traditional college algebra, studio college algebra, or maybe a different course entirely. Maybe they were ready for Trig or Calc 1, or maybe they should do intermediate algebra. So she was able to do that with her work as well. With regard to the Bailout or the intervention program, University of Michigan offers a very similar class to this Bailout Precalculus. And in fact, the format is almost identical. Students who do poorly on the first and midterm are given a chance to switch into this pre-calc class, all their records erased. And they found that students who did choose this path ended up having a higher average the next time they took calculus, as opposed to the students that simply failed Calc 1 and then tried it again. So that course had some form of success. And finally, another similar study I found to the one that I was going to conduct was done at Colorado State in 2010. It's similar to the University of Michigan Bailout course, only the course was less pre-calculus and it was more a class on functions, like trying to get students to understand functions, because that's another stumbling block that is common in calculus. And after taking this class, students tended to have a more positive outlook on mathematics as a whole, though unfortunately they weren't especially more likely to do well in calculus in the future. Okay, so that's sort of the precedent for the study. So now I'm going to go into what I did exactly. So I'm going to begin by going over how I did this data mining on Calculus 1. So this is kind of the summary here. I collected the data, I normalized and reduced the dimension of the data for reasons I'll explain shortly. I used my clustering algorithms to break the students into groups. I interviewed students from each cluster to find out the qualitative data, get like the personality of typical students, and I came up with descriptions of these clusters. So that's kind of the general procedure. Okay, so the first thing I did was I created a matrix A where each row corresponded to a student and each column corresponded to an assignment. It's exactly what it would look like if you had a grade sheet in Excel. That's essentially what that was. I inputted the scores, and then I normalized each assignment because, for example, exams were out of 100 points, whereas homeworks were out of 10, so it would be unfair to compare those just straight up. So I made all of the assignments have a mean of 0 for the score and a standard deviation of 1. Okay, then I reduced the dimension of the data. So the dimension of the data is equal to how many different assignments and attendance values I have for each student. And typically this ranged anywhere from 6 to, I think I had 29 dimensions or assignments of data before the first midterm. Now, what's the problem with using 6 to 29 dimensional data? Well, I answer that with a question. What percentage of points are on the outer 10% of a disk of dimension D? So if I have something like this, maybe a circle or an annulus, what percentage of the area of the circle is this outer 10% if this has a radius of 1? And this depends entirely, of course, on the dimension of this disk. And it's expressed in this formula right here. Here we have the total area, and then here we subtract off the area if you only use 90% of the radius, and then we divide by the total area, and this simplifies down to 1 minus 0.9 to the d. Now, anyone who's mathematically inclined can see what's going to happen as the dimension grows large. What is this quantity going to tend to as d grows big? It's going to be 1. That's right. So as d gets large, a higher and higher percentage of the students are on the outer rim of this cluster. All right, so what's the big deal about that? Well, suppose I have the center of the cluster, and maybe I had an error in that. Maybe the true value of it is over here. So as this moves, so does the points that are close to it. And by moving that, the ones on the outer 10% leave when this moves, but then I end up gaining ones that probably shouldn't be in there. And this isn't a big deal unless many points are on the outside of your cluster. So it leads to instability if you have your dimensions being too high. So how did I reduce the dimensions of my data? I used this form called singular value decomposition. I took that matrix A I mentioned earlier with the spreadsheet, and I wrote it in this form right here. Okay, big deal. Why did I do that? What's the benefit of that? Well, in particular, I used kind of a lighter form of singular value decomposition, truncated SVD, where I approximated my matrix A, which is normally n by m, with an n by r matrix, where r is less than m. R is the new, smaller dimension. And okay, and you write it in this form as a product of these matrices right here. What's the big deal with that? Well, it turns out that singular value decomposition is the best r-dimensional approximation, or sorry, it preserves the most variance out of reducing the rank of your approximation down to r. So I wanted to have as much variance remaining in my data as possible, because I don't want to just blindly chop off columns of my matrix. I want to do so sensibly, so I keep a lot of the variance and differences among the students. And singular value decomposition allows me to do this in the best possible way. I have a proof for this, but it's too big to fit in the margins of this presentation, so it'll be omitted. In addition to this, SVD is computationally easy. Every computing language I know has some package for it already. And you could also take a look at these matrices it decomposes into and gain information from those as well. So it's a very useful form to put my matrix in. Okay, so now that I've reduced the dimension and I've normalized everything, now I'm going to begin the clustering. So I used two clustering algorithms in my research. I used one called agglomerative nesting, which is known as Agnes, and I used PAM, which stands for partitioning about medoids. Okay, two clustering techniques. Why didn't I just pick one of those and just use that instead? I'll get to that in a moment. The reason why I did that is because Agnes is better for determining how many clusters I should have altogether, and then once I know that number of clusters, I can input that information into PAM, and PAM will determine which students are in each cluster. Okay, so here's how Agnes works in a nutshell. So you begin by finding the two closest points in the data set. And what you do is you're like, okay, you guys are really close together. You are now a cluster. And then what I do is I find the next two closest points, and I'm like, okay, you guys are a cluster. And I just keep doing that over and over again. But sometimes you may have a point that's close to a point that's already in a cluster. In that case, you would use sort of the weighted average of all of the points already in the cluster to determine the location of that cluster as a whole. So that's kind of that would be what would happen in that case. But you continue this algorithm over and over and over again until all the points are in one single cluster. Okay, well, why would I do that? You know, like, what's the point of just saying, oh, you're all in one big group, game over? Well, what you really do with Agnes is once you see that a point has to move really far to connect with a cluster, you cut it off. You're like, okay, if I have to move this far, you're probably in different clusters. So I'm just going to end the algorithm at this point once the distance becomes large enough. So that's how I use Agnes to determine how many clusters there are. Okay, so that worked out pretty well. So I got all these clusters, and I know how many there are. Why can't I just use those clusters that I created with Agnes? Well, it turns out that Agnes is what's known as a nearest neighbor algorithm, meaning it depends on the precise locations of where your points are. And if you were to tweak one of those points a little bit, maybe it'll be closer to another point, and I would have grouped it up differently as I went along. So a tiny change in the beginning of the procedure can totally affect what's going to happen later on. So it's unstable in that sense. So it'd be unwise to use the specific compositions of the clusters in Agnes for my work. But it is good at determining how many there are. Okay, now for PAM, I'm going to use that to determine which students are actually in which group. Now the PAM algorithm is a bit more complicated than Agnes. For those of you who may know what the k-means algorithm is, it's very similar to that, only it relies more on medians as opposed to centroids. So PAM consists of two different stages called build and swap. So when you, in the build stage, you select the first few medoids, or you can think of those as centers of the clusters that you're going to do. And you pick those based on having the lowest total dissimilarity from all the points. But maybe those initial points that you selected aren't the optimal ones. Then what you do is you begin the swap algorithm where you pretend as if one of the medoids you already had is switched with another point. And you see if the new medoid is better at being a center than the old one. If it is, you swap it and that's a new center. But if you run through all of the possible swaps and there's no better way to do things, then your algorithm is finished and you have the clustering. All right, now the advantage of PAM is its stability. Unlike Agnes, it's not a nearest neighbor algorithm, so it's not susceptible to the problem I previously mentioned. But the downside is that you need to know how many clusters there are going to be ahead of time. Now I could be like, I feel like calculus probably has, say, 4 clusters, but that's not really based on anything coming from the data, which is why I used Agnes to choose that. And the downside is that swapping thing can be computationally expensive, but I didn't really have enough data points for that to be a significant issue. Okay, so provided I've done all this, I have all the clusters and I know which students are in each one. Now at this point, I've only clustered them based on their scores in the course. Now I'm making the assumption that students who behave similarly with respect to their assignments and grades may have similar mindsets and views when it comes to mathematics and school in general. I'm hoping that, and I use the interviews with students from each cluster to see if that's accurate, and if it is accurate, what are the commonalities among each of the clusters. All these interviews required IRB approval, since technically interviewing students counts as human research. So I had to go through a lot of paperwork because I was doing human, or like research with human experiments. So, you know, it was yeah, yeah, it was a pain. Students receive $15 for participating in a 10 to 20 minute interview, which you may think is a good deal, but I don't know if the students agree with that. And I usually solicited the students by either sending an email, either through me or the coordinator of the course, or I went into their lecture, or I think I also went into a few recitations and I said what I was doing and I would pay them money to come in and talk with me. So that's how I conducted the interviews. And here are some sample questions that I asked during the interviews. I asked questions that are specific to Calculus 1, but then I also tried to get their opinions on math in general as well. Okay, so that's the general procedure for the data mining part of my work. So here's what actually happened when I did this. So I did this for the first time in the spring of 2016, but I only ran the numerical simulations to kind of get it was a pilot study to get a feel for how to do these algorithms. There were 301 students who finished the first exam. There were some students who just dropped before the first exam, or there were students who didn't show up to the first exam, so I didn't include those in the clustering. Now, in this semester in particular, exam 1 was held very early. I think it was held in the first week of September, and our semesters here typically begin maybe about a week and a half before the end of August. So there was only about 2 weeks of class time before the first exam, and consequently they only had 3 online homeworks, 2 written homeworks, and the midterm itself for me to gauge what clusters they're in. So it's 6 dimensions, not really a lot of data, but I tried to make the best of it. And so what I did was I ran Agnes, and I determined that there were 4 clusters for all this data. So here's some of the images from the data. These are the singular values from my singular value decomposition. What this chart means is it tells how relevant or how much variance each dimension of the data is capturing. So you always get a really high value for the first singular value, and in educational data sets, that dimension corresponds roughly to how well did the student do in the class. I mean, that'd be a very important thing to know if you're trying to partition them. But then they kind of like level off in relevance over time. And you usually try to look for what's known as the elbow of the data. So like when this kind of like levels off, you know you're not really getting much by including the dimensions out here. So for this one in particular, I decided to use 3 dimensions for my data. This scary looking thing is known as a dendrogram, and this is kind of a pictorial representation of how Agnes worked. So you can see these like little mushy things at the bottom are actually the numbers of students, and these tiny little thin lines are when 2 students were lumped together in a cluster. And I mentioned that at some point you cut off Agnes. What you do is you kind of go up here, and this roughly tells you how far each point had to move to be included in the cluster. And so what you do is you're like, oh, I don't want them to really travel farther than this. They're probably not in a cluster at that point. So you make a decision to cut it off here, and then you kind of almost move your hand across here, and however many clumps of students there are, that's how many you're going to use. So for example, if I did it here, there's this one humongous cluster here, there's this one right here, and then there's this one here and this one there. So there'd be 4 clusters based on this plot. And then this is a image of where the students are in terms of their assignments. And so I used 3 dimensions of data, so this kind of crushed down the clusters to 2 dimensions. So that's why you see these circles overlapping, even though each circle represents a disjoint cluster. And it's a little difficult to see, but you can kind of see that one cluster down here definitely had a significantly large proportion of the students. And this was something that I observed every time I performed this analysis. There are a lot of students in one cluster. Okay, so what were the results of this? I couldn't interview anyone, so I didn't really get a good vibe on the personality of the cluster. These clusters ended up being somewhat unstable except for the 4th one. And what do I mean by that? I ran this analysis after the first midterm when I only had 6 data points, and then I ran this analysis again at the end of the semester when I had all of their scores. And so that was more or less what I was kind of comparing to gauge the accuracy of doing this when I only have 6 data points. And for these 2 clusters at least, the majority of the people, say, in group 3 remained in group 3 at the end of the semester. And especially with group 4, they were very consistently staying in that group. Although groups 1 and 2 tended to kind of split up. Like if you were in group 1 at the first exam, these are the probabilities that you'll be in the other groups at the end of the semester. So those clusters were a bit less stable. But group 4 was very stable. Let's see here. Oh yeah, and then the thing I wanted to mention about group 4 was I looked into that. I was like, okay, what kind of students are in group 4? And group 4 tended to be the students that were struggling in the course. They had an average of 7% lower on the first midterm, like a 68% average as opposed to a 75% average. And they were much less likely to get a C or better in the course. I think 11 of them got an F, 10 of them ended up getting a D, I think 6 or 7 ended up getting a C, and then like 5 Bs and 1 A at the end of the semester. So this was definitely the group that had some issues. So I was able to detect that, and it was stable. Well, I guess unfortunately for them, if you began failing, they ended up staying that way, but it does show that I was able to detect those students. Okay, so I did this study in earnest in the fall of 2016, and this time I had more students because there were more students who enrolled in the fall semester, and I also had the opportunity to interview students. Now, there were 784 students total in Calculus 1, but I was only able to get 449 students that had an attendance in first midterm data because the attendance data was really sparse. There were a lot of attendance that wasn't handed in. Now this time, the first midterm was a bit later, so they had 4 written homeworks, 6 online homeworks, and then 10 days worth of attendance in the midterm. So this is 21 dimensions of data. Now you'll notice that there are 10 homeworks between written and online, and then there are 10 days of attendance. And I mentioned earlier that I normalized all this, so they're all kind of on equal footing, each assignment. That means that roughly half of how I'm gauging a student is based on attendance. And attendance is important for understanding students, but I figure that that may be overkill. I don't want to base my clusters too heavily on attendance. So what I did was I decided to, in addition to running the analysis just normally where I considered each day's worth of attendance, I also ran the analysis where I just combined each week's worth of attendance into one data point. So I had 5 instead of 10 because they met twice a week. And then I also ran it again where I coalesced all 10 attendance days into just one value, their total attendance. And after running this analysis several times, looking at the compositions of the clusters, I decided to go with just using the single entry for attendance. When I did it the other ways, there were often times where one cluster had like 12 students and another cluster had like 300. So there was no reasonable way that I was going to be able to find enough students to interview for the cluster that had 12. So that's why I ended up choosing the single entry, because it had the most balanced sizes of the clusters. Okay, and again, here's the singular value chart. You can kind of see that the elbow of the data kind of starts here at 4, so I used 4 dimensions for this data. Here's the dendrogram again, and you can see this time it's even more extreme how many students are in one cluster. And you can also see that here. These are all little triangles, and yeah, the vast majority, or not the vast majority, but the majority of students were in one cluster. Whereas some of the smaller clusters, represented by these bigger circles, they're a lot more spread out and there are fewer students. Okay, so I did this and then I wanted to interview the 20 most typical students from each cluster. Meaning I looked at the medoid of each cluster, which was a student that was said to be the most typical person in that cluster, and I tried to find students that had a very similar set of scores to them, so I could kind of get like typical examples of being in each cluster. So I solicited the 20 most typical for each. I think I did 5 students from each cluster, so I solicited 20 of them. Only 3 of them replied to my summons, so I didn't really get a lot of data. So I was like, okay, well, if I can't get the most typical ones, maybe I'll try and ask all of them. So I asked all 400 and, how much did I say? 449 students that I had data on to come in, and I had 18 of them. So, and I was like offering them $15, and I was like, I never had an interview going over 20 minutes, but still, and among the students who signed up, a third of them just didn't show up. So it was very difficult to get qualitative data due to non-response for this. Also, the largest cluster, the kind of mush right here, one cluster had 196 out of the 449 students. And unfortunately, this was one of the better scenarios. There were clusterings I looked at that had about 300 out of the 449 in one cluster. And they also made up 77.8% of the interviews, where despite the size of this cluster, it's still overrepresented in the interviews. So I did have some difficulties getting these interviews. But I get to learn some information, although you'll notice the meager sample sizes here. Cluster 1 had 2 students participate. They were both doing well in class. They valued problem-solving skills, and they had an above-average amount of study time, which was 4 to 6 hours compared to the median of 2 hours, which I found. Cluster 3 also had 2 students participate. They were not as enthusiastic about mathematics, but despite this, they were doing well in the course, and they viewed math purely as a practical tool. Cluster 2, I was not able to find anyone to come in despite asking the whole class. And cluster 4 made up the other 14 participants, but they were such a large sample that they had such varied answers that I really wasn't able to determine very much from looking at their interviews. Okay, and then I repeated this study one more time the following semester in the spring of 2017. This time I had a lot better attendance records, so 341 students took the first exam and had complete attendance data, and this is very close to the actual size of the class, because Calculus 1 courses in the spring are smaller. This time there were 7 online homeworks, 4 written homeworks, and 8 days of attendance before the first midterm. And I did the same thing as the previous semester. I looked at a bunch of different scenarios, and I found that this time, using the daily attendance as individual scores ended up producing the most coherent clusters. Here's the singular values again. I think I decided to truncate my dimensions at 3 because then they definitely started to level off there. Once again, I found that there were 4 clusters based on Agnes. So if I kind of cut it off right here, there's 1, 2, 3, and then 4. And then here's the PAM plot. And once again, you see that kind of clump of students in the very large group. OK. So yeah, and as before, every time I ran this analysis, it was the same story every time. There were 2 medium-sized clusters, 1 small cluster was about 10% of the students, and then the rest of them were in one of the clusters. Okay. Now, I learned my lesson from the previous semester, and this time I decided to have students complete online surveys rather than having to come into Cardwell to give me information. I collected 43 usable surveys. Some students viewed it as a joke, and I couldn't use their data. And this time I actually got at least a few students from each one of the clusters, so this ended up going a bit better. Cluster 1 didn't really seem to have a lot of distinctive features, although they were more likely to be freshmen than was typical, and they all kind of expressed doing well in Calculus 2 as their motivation for doing well in Calculus 1. Cluster 2 was the smallest cluster. They had a pretty negative view of math overall. In fact, I think this was, let's see, was this the cluster? Yeah, there was one student who wrote a giant essay about how much they didn't really like Calculus 1. So that these students did have a negative view of it, and they gave passing as their primary motivation. Again, I had the same issue with cluster 3 as I did with the large cluster last time. There were just too many people, highly varied answers. I didn't really see many commonalities among them. Cluster 4 was probably the most consistent cluster when it came to personality that I found. They were overwhelmingly likely to cite higher earning potential as a motivation. They did want to get through the class, and they were pessimistic about it. They thought they weren't going to do well, but despite this, they were mostly getting A's in the class. So that seemed to be their personality. Okay, so the conclusion from all this is that Calculus 1 is likely a homogeneous class. Every single cluster that I ran ended up having a massive amount of students in one cluster. And that kind of suggests that many Calculus 1 students behave the same way, at least when it comes to their assignments, but then also with the interviews, they gave very homogeneous answers overall. And the sort of profile of a calculus student is that the majority of them are freshmen. They have a positive view of math overall, but it was mostly used as a tool for their profession. They prefer recitation to lectures, and they almost exclusively use practice exams to study. The majority of Calculus 1 students I've seen satisfies all 4 of those. But there's another useful result from what I've done. In the first semester that I did this, I was able to detect the at-risk students very early on in the semester with only 6 data points. So it does show that the data mining does have the potential to detect at-risk students. Okay. So that was the data mining portion of my research. And then this is the intervention portion of my research where I looked at bailout pre-calculus. So another one of Dr. Bennett's previous students, Drew Cousineau, discovered that within the first few weeks of a course, students become set in their ways. And they're unlikely to change how they study and how they approach the class, even when confronted with poor grades. Now, intervention courses are good because they can sort of provide a strong reset to these habits that they're beginning to form, and they can give students another chance to do well and get them back on track. Okay, so let me describe Bailout Precalculus, the particular intervention course I'm going to be discussing, in more detail. So this began at Kansas State in the fall of 2013. And as I mentioned earlier, if a student does poorly on the first exam, meaning they get a D or an F, they're invited to switch into this new pre-calculus class. So the dean's office backdates a withdrawal from the course, so it appears on paper that they never took the course at all. And in fact, since Bailout Precalculus is listed as a 3-credit course, they're actually reimbursed the tuition for the 1 credit hour that they're losing, which is a nice boon. And they can spend the rest of the semester, which is typically about 10 weeks, reviewing the material that they did poorly in Calculus 1, but then also shoring up their algebra and trig skills. So this class format is a little less intense than Calculus 1. It meets twice a week during the old Calc 1 lecture time, so there's no chance of a scheduling conflict. It's a 3-credit course, and the good thing about it is that it's a small class. The first semester it was run, there was only 1 section and about more than 30 students, so it was a little large at that time. But every other semester we've had has at least 2 sections, so the classes are at most 30 students. So it's definitely a lot different than the large lectures. And the class, the day-to-day functioning of this class is a lot more like a high school course, more so than a typical college one. The professor typically did give some like mini lecture presentation in the beginning or maybe the first half, but there usually was some sort of time for students to kind of work on doing problems or practicing the material, which is a lot more similar to high school as opposed to calculus, where you just have, or college, where you have to just absorb the material. So now, this is a pre-calculus course, but it's a little bit different from many other pre-calculus courses. Rather than just being a pure algebra and trig review, this course had an emphasis on getting students to be able to manipulate expressions into more convenient forms, which is an important skill for succeeding in calculus, and one that students often don't have. So for example, these are some questions that students may encounter in this Bailout pre-calculus. Like for example, let's say you have 3t over 2 as an integrand, and you want to do a u substitution, and in your substitution you want to see a 2t appear in your integral. Well, you want to see if you can manipulate this to a more convenient form. Or maybe you're taking a limit as t goes to 0 of this, and you want to exploit this identity right here, but you need to know what the leftovers are going to be. And they have similar phenomenon with trig. Like for example, that could also be used as a technique in u substitution for an integral. Okay, so that's the format of the class. Now, what did this class do? What was the impact of Bailout pre-calculus? The most notable impact is the effect it had on retention, not in STEM fields or in calculus, but in the university as a whole. So 85% of the students who bailed out, I forgot to put this, but it was in the year 2013, remained in the university after 1 year, compared to only 41% of those who ended up failing calculus in that semester, but they elected not to switch into Bailout pre-calculus. And by the way, typically about 40% of students solicited end up choosing to switch into Bailout pre-calculus. So even though it's a good deal, not everyone chooses to select that path. Now, one issue with this, so this is a pretty drastic difference, but if you think about it, students who are likely to elect to take Bailout pre-calculus may be a bit more proactive in general about their college career, so they may be a little more invested in it and consequently may be more likely to stay. And so that would be just based on the types of students who enroll in Bailout pre-calculus to begin with, not necessarily the effect of the course. So to combat this selection bias, we compared the students in 2012, the year before this began, who failed, compared to the combined population of the students who just failed calc in 2013, combined with the students who bailed out. So we were kind of viewing the impact of this course on the total population. But even considering this, 55% of the students remained in the bail plus fail group, whereas only 51% remained for the 2012 group, and this was a significant result. Unfortunately, the effects on the actual performance in calculus wasn't as strong as the effects on retention in the university overall. So again, we compared the students who simply failed calculus in 2012, and I'm using the data from 2014 here because in this year we were able to accommodate every student who wanted to switch in to Bailout, whereas in 2013 we were not able to do that. So I figured 2014 would be a more typical year to look at. In 2012, there were 94 students who failed Calculus 1. There were 32 who retook it and passed it within the next year, and 25 of those 32 who passed ended up getting a C or better. Now, if you look at the population of the students who bailed, 19 out of 44 retook and passed, and 15 got a C or better. And if you just look at the proportions of only the first two columns, it appears that Bailout pre-calculus did do a good job at getting students to do better in calculus. But again, with Bailout pre-calculus, a lot of the students just elected to not take calculus again, period. Many of them ended up switching their majors at the same time that they switched into the Bailout course, so they weren't even going to bother taking Calc 1 anyway. So to combat this, again, we looked at the combined population, and the proportions really weren't as significant as they were for the overall retention. Okay, so to understand what was going on with Bailout pre-calculus, I wanted to see what the students' thoughts were, especially since I claimed that there would be some sort of psychological boost to these students. So I invited these students in for interviews, and unlike Calculus 1, they were a lot more likely to come in for interviews. I had 18 participants out of the roughly 60 people I asked to interview, which is compared to the 18 out of 449 that I asked the other time. So they're a bit more willing to share their experiences. And again, I offered $15 for participating, and I solicited them actually in the class itself. So I went into a session. I was like, hey, I'm doing this study. Come in. But then I also recruited some students from previous years. So it's only offered in the fall. So I found 6 students from the fall of 2016 and fall of 2015 to invite in as well, to kind of get some a more diverse representation, since teachers change over time and sometimes the content of the course does as well. Okay. Uh-oh. There we go. Whew, that was scary. I'll just have to turn this around. Okay, so I interviewed these students. What happened? So the students in this course almost exclusively viewed calculus as a problem-solving tool. And again, this isn't particularly surprising. This is the view that most calculus students have, although students that I interviewed previously in Calculus 1 were a little bit more likely to mention the less applied aspects of mathematics. Half of the students interviewed claimed that Precalculus improved their opinion on math, which is pretty significant since these people were likely to be jaded about math since they just did poorly in a math course. So that was pretty significant. Students frequently mentioned that they had more confidence in their mathematical abilities upon taking the course. They had opportunities to review things they were doing poorly in, and they had more personal actions with instructors so they can get help for things they needed. And yeah, and that's the last point. Since it was only a 30-ish student class, it was a lot easier to ask questions, which is something that many students lamented that they couldn't do in large lectures. So what happened with their majors? So it turns out that half of the students ended up switching their major to something that no longer required Calculus 1, which was actually pretty consistent with these results here. About only half of them retook and passed in the future. But many of the ones who didn't remain in a major that require Calc 1 did require some form of math, like perhaps like business calculus. So many of them did end up taking math courses in the future. Bailout students were more likely to be older than typical Calc 1 students. The vast majority of Calc 1 students are freshmen, whereas only about half of the students in Bailout are freshmen, which is significantly lower. And they're also much likely to have not taken calculus in a prior semester. So many students enrolling in Calc 1 have had either AP calculus before, or maybe they're retaking it again. But students who switch into Bailout pre-calculus had by and large, had no experience before. And then many students, to piggyback off of this, many students expressed the fact that they were intimidated by seeing their peers in class know a lot of the calculus material already. So this kind of demoralized them when they were in Calculus 1. Students overwhelmingly had a positive view of pre-calculus as a whole, and some of the reasons are smaller classes, ability to ask questions, and they had an opportunity to review as opposed to blazing ahead in Calculus 1. And among the older students, it was impossible to gauge this for the 2017 students because they were in the actual class. But 5 out of the 6 students who used to be in Bailout pre-calculus the previous semester ended up taking a math class in the future. Okay, so when asked to rate how impactful they believe Bailout calculus to be on their own college career, students in the most recent semester gave a 2.92 out of 5, which is pretty good. But then the students who answered the same questions, who were some of the older students from 2015, 2016, gave an average of 3.83 students. And again, this is a small sample size, but this suggests that over time, after they've already had this class and after they've seen the effects of it, they are appreciative of the impact this had. In fact, I actually had one student who wanted to perform an interview with me when I just solicited the 2015-2016 students. She wanted to do a Skype interview because she was so excited to share her experience with this class, even though she lived in Connecticut. So they do have some very enthusiastic fans of this class. Okay, so what do we get from all this? As I showed earlier, it has a positive impact on retention in the university as a whole. Students who take this class are more likely to gain confidence in their abilities and have more time to adjust to the transition from high school to college. And student appreciation of this course is strong and grows over time. Okay, so that's what I did. So let's go back to those research questions that I posed in the beginning. So remember, my first one is that Calc 1 is a large lecture. Can I use data mining to break the students up into clusters? And if so, can I differentiate instruction? And what type of clusters would these be? So unfortunately, data mining did not reveal as much about Calculus 1 as it did for Studio College Algebra. Rachel Manspeaker didn't have the same issue that I did with having a huge percentage of the students all in one group. And she was able to determine more information about the clusters than I was able to for Calculus 1. And the reason for this could be, as I mentioned earlier, Calc 1 could just truly be a very homogeneous class, which reflects the experience of many people who have taught the class or been involved with it in some way. However, this study had access to less data than was available in that work, so that could be a factor as well. I didn't have how students did on individual exam questions on the midterm, for example, which was something that was available back then, and I didn't have as much attendance data. So that could be a factor as well for why I wasn't able to find as many sensible clusters. All right, so the second question is that can we quickly identify students that are struggling, and is Bailout Precalculus a good way of helping those students that are struggling? And the answer is, based on the spring of 2016 work, yes, it is possible to detect students who are failing early on in the semester. And as for Bailout Precalculus, as I just mentioned a few minutes ago, Bailout Precalculus does have a good track record of not only giving students competence, increasing their mathematical abilities, but it also makes them more likely to stay in the university. And for the last question, if it is effective, which it was, at changing the trajectory of students' progress, why is it effective? And based on the interviews, I hypothesized, or I surmised that students gain increased confidence in their abilities, which more confidence leads to a more likely, a higher likelihood of success. They're more likely to feel supported by the school. So this isn't a class that's offered at every school. Like, a lot of schools don't have, in fact, it's actually uncommon to see a course of this format somewhere else. So they felt that the fact that they had a second chance and that they had more personal attention from the instructors, they felt more positively about the school as a whole. And it also, this course provides us an easier transition from high school to college. They get kind of get to be worked in through taking this high schoolish class, and then maybe after they get used to being in the university as a whole, then they could be prepared for the large lectures to come. Okay, so are there any further avenues for this research, or what are the implications of what I've done? One thing that could be done is looking at the data mining in other courses. For example, the Calc 1 and College Algebra aren't the only large lecture courses out there. For example, there are things like trigonometry or things like that this could be investigated in those. Also, this was done at Kansas State University, which is a large public research institution. So if you performed this clustering somewhere else, or even looked at the Bailout Precalculus somewhere else, you may get different results based on the type of school and the type of students that enroll there. But even among other large research institutions, you may see some differences if this was performed elsewhere. So it'd be interesting to see other schools' experiences with having something like this. Back about 20 slides, I had those questions from Precalculus, those kind of more unorthodox questions. I didn't investigate specifically how effective those were at promoting student understanding, but that would be an interesting investigation. Would those promote understanding above more traditional questions? And finally, during a lot of my interviews, this isn't as much an avenue for research as it is for policy, but many students, or at least a few, suggested that they wanted Precalculus as just a regular year-long course, because that's not how it is here at K-State. Precalculus is only offered in the Bailout version. Typically, if students need more background, they're advised to either take trigonometry or maybe do a full year of college algebra or trigonometry, or the advisor's just like, you'll do fine, and then they just kind of throw them into Calculus 1. So perhaps having this course permanently could be good for situations like that. All right, well, that's all I have. Thank you very much. Any audience questions?
So I have kind of a technical question. So in the Agnes algorithm that you used to determine the number of clusters that you needed, from what it seemed like to me, you had sort of like a parameter that you used as like a upper bound for how far you wanted the points to move. How did you determine what that should be?
There's no like satisfying answer to that. You just sort of look at the plot and try to make the cleanest division possible. So yeah, I did try to use data mining in my research because I think it kind of brings out what's naturally in the data as opposed to me just asserting that things are true. But sometimes you do need to make subjective judgments. Yeah. But I did try doing a bunch of different configurations with different numbers of clusters, different dimensions of data and things like that. And the ones I presented today were the ones I thought made the most sense after looking at a bunch of them.
When you counted the number of attendants, was it just to lecture or recitation?
It was just a recitation.
Oh, just a recitation. Right?
Yeah. So yeah, it was a gauge on whether they attended recitation. Yeah. Each semester I found 4 clusters to make the most sense. Yeah, typically when I went above 4 clusters, I was hoping it would kind of split up the larger cluster into something more sensible. It actually almost always split up the smallest cluster. So like the cluster of 40 students ended up being like 12 and 28, like afterwards. So yeah, 4 typically made the most sense. Yes, so yeah, there are varying instructors for each semester. Yeah.
So if you had to make a prediction about other universities outside of K-State in different regional areas, just a different student body, could you say what you think, or possibly also smaller class size, what those, like, it seems like there was a strong bend toward a clustering of cluster 4s. Do you think there would be potentially a cluster with different characteristics? Different school that would have a strong bend in the same way?
I think that very well could happen. Again, like the homogeneity could just be due to me not having enough like robust enough data as opposed to my predecessor. But I wouldn't be surprised if the results were pretty similar if I went to an institution similar to K-State, for example, like a Midwest large research institution. I suspect it'd be mostly the same, but if I went to a school in like a different region of the country, or I went to a school where students typically have a stronger or maybe weaker background, then I would expect the clusters to be pretty different.
What major are most students in calculus?
Well, by and large, there's some form of engineering. I think it was about 80% of them that are engineers coming in, which everyone's seen that.
So piggybacking on that question, what do you think, what if we went to a school that didn't have an engineering program?
Yeah, it could very well be different then. I suspect that there would be a lot fewer answers of just viewing math as just a pure tool. And I suspect that like the personality of these clusters would be pretty different if there wasn't that. Oh, yeah.
Sorry, I didn't catch the second round because of the, I don't know, but I got the impression that in your like first round of data, the very stable group was group 4 and it was the group that was struggling.
Mm-hmm, that's right.
So was because in the other round of data, was it group 3 that was the large cluster? Or did
The number, yeah, like so groups 1, 2, 3, and 4, like they're likely very different students depending on the semester. Okay. So I wouldn't compare cluster 1 in one semester to cluster 1 in another. Yeah, and so in Dr. Manspeaker's research, who did this with college algebra, she was able to get enough of a sense of the personality of each group to give them kind of a fun name, like what were they? Overachievers. Sisyphean strivers were the ones who tried really hard but like couldn't quite make it, and there were like the employees who viewed college algebra as like a low-paying job. But I would have given I would have given the descriptive names like those, but unfortunately in most cases I wasn't able to come up with enough of the personality of each of the clusters to do so.
Why do you know, or did I just miss why Dr. Manspeaker was able to get more of a sense of the personality of each cluster in studying studio college algebra versus PAM 1?
Well, she did have a better response rate with interviews, was for one, and also the clusters were more balanced in size. So sometimes